So Kamalika received a bachelor degree of technology in computer science and engineering in 2002 from Indian Institute of Technology, Kanpur, and a PhD in computer science from the UC Berkeley in 2007. And after a postdoc at the Information Theory and Application Center at UC San Diego, she joined the CSE department at UC San Diego as an assistant professor. And I guess she's associate professor now. She received an NSF Career Award in 2013 and the Hellman Faculty Fellowship in 2012. Kamalika's research interests are the foundation of trustworthy machine learning, which includes problems such as learning from sensitive data while preserving privacy, learning under sampling bias, and in the presence of an adversary. She's particularly interested in privacy-preserving machine learning, which addresses how to learn good models and predictors from sensitive data while preserving the privacy of individuals. And I also like to mention it was my great honor to have her as my PhD advisor at UC San Diego.
I'm very glad you mentioned it. No, it was great to have Shuang. It was great to work with Shuang. I'm sure all of you guys know.
Thank you.
Okay, so let's get started. So what I will be talking about is kind of, just basically, I would call it some experiments in privacy definitions, right? So, a lot of you, almost all of you guys probably work on differential privacy, and, there's been a lot of progress in differential privacy, algorithm design and machine learning and so on. But one of the things that I've been doing for the last couple of years, we've been also working on standard differentially private machine learning, but some of the things that we've been doing is kind of experimenting with definitions a little bit, and trying to see, in some sense it's a theoretical study in if you modify definitions in certain ways, what kind of properties can you get, what can you get, what can you not get, what do you lose, what do you gain, and and this is joint work with my student Joseph Gemlek and Joseph Gemlek and Jacob Vimola and my collaborator Ashwin. Okay, so as you all know that for data privacy style problems, there are really kind of two main styles of rigorous privacy definitions that have emerged. So, of course, the most popular one, which is basically the gold standard right now, is differential privacy. But on the other hand, we also have what is called inferential privacy, right? So, what is the difference? In inferential privacy, the idea is the following. There is some prior knowledge. The adversary has some prior knowledge. There is some private release, some release based on sensitive data. And then the adversary can combine their prior knowledge based on this private release to get some posterior knowledge, right? And what inferential privacy says is, given, in this process, for certain classes of adversaries, their posterior knowledge should be more or less the same as their, right? And this is, as you can see, this is not always satisfiable for arbitrary adversary classes. In fact, there are theorems which say that you can't, if your adversary can have arbitrary prior knowledge, there is nothing you can do. I mean, even releasing a single bit can just, they can just learn everything. So you have to choose your adversary class properly. And then you have to also choose some sort of a distinct user class where, there are some users who are learning something, but some adversaries who know some things, they're not learning much more. So the definition has to be set up properly. But there are cases where this kind of thing can be used. Okay? And then on the other hand, there are the definitions such as differential privacy. And here the idea is that, kind of in the classical definition of differential privacy, the idea is that the participation of a single person in the data does not change the probability of an outcome, right? And here you have a randomized algorithm. So that's where the probability comes from. So what this means is that whether Alice participated in data set, or if you took Alice out of your data set and you pushed, and you put Bob in instead, then the probability, then the, then and then you have a randomized algorithm which was outputting something on that data. Then because it's a randomized algorithm, its distribution comes from an output. And what this means is that these two output distributions would be similar, right? So in one case or one world, if you might call it, Alice is in the data set. In another world, what happens is Alice comes out and Bob goes in instead. In both cases, the distribution of the outputs is right? And there is also a more general version of this called couple worlds privacy, which looks at it in the general. Okay? And as you also all know, the trade-offs in data privacy is that there is, in general, we see a three-way trade-off. On one side, you have privacy. So, this is, kind of in the individual level privacy. I'm going to back to the individual level privacy. That on one, so there's a three-way trade-off. On one side is privacy, on the other side is accuracy, and on the third corner of the triangle is data size or number of people, right? So you can get two vertices of this triangle, but not all three. So if you want privacy and accuracy, you can get it, but you will need to have more people. And the same thing. You can get privacy with small data sizes, but you would have to sacrifice that accuracy and vice versa, right? And in the middle of the triangle, so what determines this? How what this triangle looks like. In the middle of this triangle is, what I would very roughly call complexity, but what it measures is how complicated is the task that you want to solve. So if you want to calculate a single statistic such as mean, right? Then your privacy, accuracy, data size trade-off, may be quite, it may be low and it may be manageable. But if you are looking to train like a deep neural network, then this trade-off, then this triangle would look somewhat different, right? So then this trade-off may be less manageable, and so on. Okay? So this is kind of what we have to do. Okay, so in this talk, what we will look at is, as I said, some experiments with, what I would largely call experiments with experimenting with the privacy definition. So in this talk, what we would look at is a variation. So we'll look at, two experiments. One related to differential privacy and the other related to inferential privacy. So for differential privacy, we would look at slight relaxation called capacity-bounded differential privacy. For inferential privacy, we would look at a relaxation that we call profound. Okay, so differential privacy, I can go very fast over the slide. Again, as I said, what this tells you is that the participation of a single individual in the data does not change the probability of any outcome by very much. And, this is interesting because from the point of view of an attacker, whatever you would get, your algorithm's output on the data plus Alice is, very similar to your algorithm's output on the data plus Bob's data. And the way this is enforced is, as I said, through these are randomized algorithms, so that output is drawn from a distribution, is to make sure that these distributions are similar. And in classical differential privacy, the way we do this is by making sure that if you change one person's value, the two distributions are close in what is called max, right? And this is kind of what it looks like. If you take the supremum over t, then the log of the absolute value of the log of probably of the likelihood that a of b equal to t, when over the likelihood that a of b prime equal to t, is absolute value is at least x. Okay. For capacity bounded differential privacy, one of the things that we start out by looking at is what happens when the adversary is bounded, right? So what kind of, so where could we see bounded adversaries? Well, one possibility is to have adversaries which are automatic, right? So if you have an automatic adversary which can violate privacy or which can do, fast hypothesis testing, that sort of an automatic adversary is, in some sense, it's much more powerful than a human because it can process a lot of stuff, right? So there's a difference between, let's say, I know something about my neighbor and I look at the output of a private algorithm and I compute something else. This sort of thing could scale a lot more if you had an automatic adversary who could do this, right? So in some sense, automatic adversaries are, in some sense, if they can violate privacy, that's in some sense is more dangerous, right? So that is, that could be one application. Another application would be data usage contracts. So, this happened to me several years ago. I do privacy, but half of my research is also on like other kinds of machine learning. And we were trying to develop this active learning algorithm, and we tried to get this data set from Stanford. And what happened was that, so we tried to get this data, there was this educational data set, and, that's an application where active learning works very well. So we tried to get this data set from Stanford. And what happened was they said, oh, sure. I mean, you send them an email and they sent me 10 pages of forms. And then the forms were like, oh, you agree to not do this, that, and the other, right? So with the data, you agree not to combine it with something else. You agree not to compute this on it, and you agree not to try to do that. So that is, what is called the data usage contract, right? So it could, so if we understood bounded adversaries, then we could also use that design data usage contract, right? So what could a bounded adversary infer? Well, then we could say that, okay, these are the things you're supposed to do, these are the things you're supposed to compute on the data, that's it. And, then if you stick to that contract, then then you are fine with privacy. But if you're violating the contract, then, then you can maybe then privacy would be right. So the thing that we are trying to do here is to model privacy against bounded adversaries. So how can we model privacy against bounded adversaries? So let's first start out with a slight relaxation of differential privacy, right? So let's say, remember how we talked about how do we measure how these distributions are different when you substitute Alice with Bob. Um, and so the way we were deciding that was to look at the max divergence, right? Now what we could do is instead of the max divergence, let's say we relax it to define tail divergence, right? So we will go back to Rennie after a little while, but so let's start with KL because KL just makes things conceptually simpler. So what we could do is we could say that, okay, so the tail divergence between A of P and A of B prime is epsilon. And why is this interesting? Because tail divergence has what is called a very nice variation. So if you have two distributions, P and Q, then the tail divergence between P and Q can be written in this particular form where f is the class of all functions. So this is the supremum over h in the class of all functions, expectation over p, h of x minus expectation over q, e to the h of x minus 1, right? And this measures so what this does is it measures how any function can tell P and Q apart, right? So this is the supremum over all functions. It measures how any function can tell P and Q apart. Now the question is, if we are, tail divergence gives a way to tell us, how any function can tell P and Q apart. So one thing we could do when we look at, when we are trying to look at capacity bounded privacy is what if we restrict a function class? Okay. So, and this leads to, and this in fact has been done before, and this leads to what is called the age-restricted tail divergence. And what you are doing over here is you can say the age-restricted tail divergence between two distributions P and Q is the supremum over all h, all functions h, in a function class capital H. And so instead of all functions in F, what you look at is all functions. So F was the class of all functions. You look at all functions in a specific function class. And you can measure how any function in A can tell P and Q. I, is that, the thing is when I'm on,
Yeah, I think there is a question on chat.
oh, there's a question, I see. This is the class of, yes, all measurable functions. Yes, you're right. This is the class of all measurable functions. Sorry for that. I guess when I'm on the play view, I can't see the chat, so I have to just sort of go back and forth. Okay, good, excellent. P and Q apart, and the good thing is that this can be defined for any F divergence. So just a quick detour, because I think some of you guys might be interested in this. So what are F divergence says? So if you have a convex function f such that f of 1 is 0, then the F divergence between two distributions P and Q can be there's an F. There should be an F in the F of dp dq. There's a typo. So the F divergence is expectation x drawn from Q, F of dp over dt, right? And these are when P is absolutely continuous with respect to Q. And there are a lot of common, the good thing is that there's a lot of common divergences that satisfy this. So for example, KL divergence is something, Jensen-Shannon, alpha divergences, and so on. And the good thing is that any F divergence has this nice variational form, right? For KL divergence, I showed you that variational form where P and Q are set apart. So any F divergence has this nice variational form. Sorry, there's a little bit of a typo. So what this should say is supremum h in F, expectation x over P, h of x minus expectation x drawn from Q, f star of h of x, right? So, remember for KL how there was this e to the h of x minus 1, that is just f star, where f comes from the F divergence, and f star is the potential conjugate. And because it has this variational form, you can restrict your function class to some class H to get corresponding restricted divergence. And for some of you who might be familiar with these generative adversarial networks, right? The way where this comes from is actually, so there are these things called FGANs, right? So FGANs are a generalization of generative adversarial networks. And what these FGANs are doing is that they are minimizing these restricted divergences. Okay. So coming back, what we can do is we can talk about age-restricted tail differential privacy, where instead of limiting the tail divergence, we can limit the age-restricted tail divergence. We can say that is at most epsilon. What about Rennie? Well, for Rennie, the quick reminder of Rennie differential privacy. So, one of the relaxations of differential privacy, which I think there's been a lot of use for, and which is very nice and clean, is Rennie differential privacy. And there the idea is that if A is an epsilon alpha Rennie differentially private algorithm, then the Rennie divergence of order alpha between A of B and A of B prime is at most epsilon, right? So that is the definition of Rennie differential privacy. And the problem, though, is that Rennie divergences are not F divergences. However, the good thing is that Rennie divergences are connected to what are called alpha divergences through a very nice closed form. And this is the closed form. So the Rennie divergence between P and Q is log of 1 plus alpha times alpha minus 1. Alpha divergence is something called an alpha divergence between P and Q divided by alpha minus 1. So it's a very nice closed form. And alpha divergences are in fact F divergences. So we can just use them to define restricted Rennie divergence just through this kind of closed form, right? So we can use it to define restricted Rennie divergences in exactly the same. Okay, so capacity bounded privacy. Now we have a way to model privacy against bounded adversaries. What can we say about its properties? So, what are some good properties of privacy definition? So, this is due to Pifar and Machinavajala. So, they talked about kind of three major properties. So, one is something called convexity. We'll talk about that in just a little bit. Two is something called graceful composition, and the third is post-processing invariance. So what does convexity mean? Convexity means is, so if you have a private data set, then what you do is, you have two algorithms, M1 and M2, which are both epsilon private, and you pick M1 with probability P, you pick M2 with probability 1 minus P, and then you release the result, right? And P does not depend on you because P is something, right? Then the result would also be epsilon. Now, what we can show for convexity is that this holds for H-bounded real privacy for any H. I mean, you need to have some very mild conditions on H just to make sure that things are good. And this actually holds for any of private. The proof just comes from the convexity of F, and it holds for any of private. No, that is kind of the second definition that we talked about was post-processing invariance, and it's actually a very useful property. So post-processing invariance means you have a private data set. Then what you do is you have some mechanism, which is epsilon differentially private. You release its, you have its output, and then you just use it to do the thing, right? So you have some epsilon differentially private mechanism. It releases something, and then you post-process it. The important thing here is that you don't go back to the private D, right? So you don't go back to D again, but you just post-process it in whatever way you please, and then the result would be epsilon private. Okay. If you think about this, if you are bound in your adversary, and if you wanted to do something a bit better than unbounded adversaries, you can't really expect to have arbitrary post-processing, right? If you have, then you will just come back. If you had arbitrary post-processing, you would basically just come back to, you will just basically come back to unrestricted adversaries, right? So, so post-processing invariance does hold, but it holds with respect to certain kinds of function classes. And in fact, what we can show is that it holds with respect to function classes G, where for any function G in G, H in H of G is an H, right? So an example where this satisfies is, let's say G and H are linear functions. Well, linear functions are linear functions, are linear functions, and so, you're okay. Right? So post-processing for any kind of definition of this sort, can't hold for arbitrary adversaries, but it will hold for adversaries in this. Okay, so finally we come to graceful composition. Graceful composition is, and here I am talking about, what is called, what we call sequential composition. So what graceful composition, let me just talk about the simplest version ever. The simplest version ever is you have a private data set and you have two algorithms, M1 and M2, that don't consult each other. M1 is epsilon differentially private, or epsilon private, right? M1, releases something that's epsilon private. M2 releases something that's epsilon private. They don't consult each other. They don't even know, M1 doesn't even know M2 exists. And both outputs are available, right? And the result is 2 epsilon, right? So this is kind of the very basic composition result. As it happens, in these cases, we can, and this is satisfied by unrestricted, the unrestricted privacy, unrestricted differential privacy, right? Unrestricted any privacy. So what we can show is that if A1 is H1 epsilon capacity bounded private and A2 is H2 epsilon capacity bounded private, then the union is H1 plus H2 2 epsilon capacity bounded private. So H1 plus H2 is essentially the Minkowski sum, right? Like, it's the sum of H1 in H in H1 and in H in H2. So it's a Minkowski sum. And that is H1 plus H2 2 epsilon capacity bounded private under somewhat mild conditions on H1 and H2. And, this might seem a little strange, but the reason why this happens is because under mild conditions on H1 and H2, the unrestricted and the restricted divergences are somewhat closely related, right? And that is kind of what we are exploiting. So, and the mild conditions relate to something like, continuous and that sort of stuff. So the mild conditions are, so like linear functions satisfy, right? So you can get this kind of capacity. Yeah. So basically, that's what we are exploiting. That the unrestricted divergences and restricted divergences are related in a certain way, and that's kind of what we're exploiting. Okay, so we talked about this definition. What about summaries? I think there's a question over here.
Kamalika, quick question. What about robustness to auxiliary side information?
Robustness to auxiliary side information. So here, so when you say robustness to auxiliary side information, what do you mean? In what way? Mathematically?
Yeah, there are multiple ways to define it, but one way is to say that if I know the prior, which I think then the bound that I hold would still hold under knowing that prior or not knowing that prior.
No, I'd have to think about it a little bit.
Okay.
I would have to think about it a little bit. Generally, the guarantee is of the sort where the participation of so generally the differential privacy guarantee is of the sort where the participation of a single person in the data does not make a difference, and it gives you the kind of guarantees that you're talking about, like inferential guarantees, when the people are one condition under which it gives you the inferential guarantees is when the people are independent. But there's also other things that you could show. Yeah, that's actually a good question. I would have to think about it a little bit. Okay. So what about mechanisms? So one special case that we could look at, and it's just kind of a simple case, is when you are looking at linear ages, because these calculations, as you can imagine, are somewhat hard to do. So one case when we can look at is something called linear tail privacy. And so if you look at a sanity check, even for something as simple as linear tail privacy, the non-private releases would blow up, right? So if you have A of D and A of D prime, the lin tail between them is actually infinity. So the non-private releases would blow up. For Laplace mechanism, you can actually do the analysis by hand. It takes a lot of algebra, but you can do it. And this is kind of what it looks like. So if you did the lin KL between two Laplace mechanisms, let's say global sensitivity 1 with parameter epsilon, your lin KL between the KL would be epsilon minus 1 plus 1 to the e to the 1 plus, epsilon minus 1 plus e to the minus epsilon. And which is not super hard to do, but the lin KL would look something like this. And it's a little bit better, especially when epsilon grows reasonably large. It's a little bit better. For Gaussian mechanisms, it's actually exactly the same. And the reason is, for Gaussian mechanisms, if you're looking at the class of all functions, right? And there is a function which achieves that supremum. If you look at the function that achieves the supremum, it's a linear function for the Gaussian mechanisms. And if you think about it, you can see this, right? Because for Gaussians, Gaussians with equal variance, the separation, the most separating function is linear, right? And that's where it all comes from intuitively, right? That So so for Gaussian functions, it's the same. Here is a lot of calculations that my student Jacob did, and here are some results. I don't want to go over I don't want to go over them in a lot of detail, but you can get improvements. They're not huge improvements. They're relatively small improvements. And again, these are all upper bounds. I mean, none of them are exact. So, these are some things that we can show, that these are improvements. These are relatively small improvements. As the dimension grows, the improvement gets a little bit better. So that's kind of where we are. So I must mention in this context that there's been several other related attempts at least theoretically coming up a framework for privacy against bounded adversaries. And actually, one of the earliest and one of the really good ones was I think Ilya was one of the authors here. Was called Computational Differential Privacy, and there they were looking at adversaries bounded by polynomial computational power. The difference between ours is a little bit simpler. There they had to show and distinguish. I mean, there the definition was actually quite fairly complex. And as I'm sure, as most of you know, you're in Google, I'm sure most of you know, if the definition is too complex, then at some point people just can't use it anymore. So it was quite a bit complex. And then I think this is also work by Peter in the audience. They looked at generative adversarial privacy, where the mechanism was some sort of minimax game between the adversary and the learner. Right, so that's another attempt. And so we experimented with a notion of privacy for bounded adversaries. One of the interesting things that we could show is that the definition retains many good properties, and we could show some better privacy parameters for the same amount of added noise. So this is this was one of the works. So maybe if next what I will do is switch to inferential privacy, but maybe this might be a good time to take any questions.
So I have a question, Kamalika, about the composition. You mentioned about composition, but is it adaptive in nature? Can you handle it?
So our result is not adaptive. It's not adaptive. There may be adaptive, may be possible, but at some point you just have to stop and write a paper. So that's actually an interesting open question. So by the way, another thing I didn't tell you guys is that there's a lot of interesting open questions here. Another thing that we managed to do was we managed to prove that this kind of capacity bounded privacy retains a certain amount of algorithmic generalization. Like differential privacy has some strong algorithmic generalization guarantees, and capacity bounded privacy retains some of that. And actually a very interesting open question is how to strengthen these guarantees. So what we could prove was a fairly weak result, but there are very strong results now on algorithmic generalization. So that's another interesting thing to look at. And adaptive composition is also another interesting thing to look at.
I see. So we cannot think of right now, let's say, using this in, let's say, DPHGD or this kind of things as of now.
Yeah.
Okay.
So for DPHGD, would you need fully adaptive? Or would partially adaptive be okay?
Yeah, it's a good question.
Right? For DPHGD, it may be okay to have just partially adaptive.
Maybe, yeah.
And there might be some, actually, speaking of open questions, there might be a good opportunity for formalizing this kind of partially adaptive composition, and that might be possible with some of the relaxed definitions.
Makes sense. Perfect.
I think by partially adaptive, Kamalika, you mean you just rely on the last release as opposed to the sequence of all releases.
Exactly. That's exactly what I mean. Yes, that's exactly what I mean. It's also, you rely on the last release. You also rely on things like, DPHGD is kind of a additive algorithm, right? You are not doing anything in between. You are just adding. Yeah, I think there are some interesting things to formalize over here. Yeah.
I think on this composition question, I mean, we would also possibly need like a version of the strong composition theorem, right? Because you mostly showed just like the graceful one with additive epsilon.
Absolutely. Yes,
Yeah.
absolutely, yes, absolutely. That is true. Yes, we haven't looked closely at that. Yes. Yeah. Okay, excellent questions. I mean, I think, yeah, excellent. Okay, so moving on, the next thing that I would like to talk about is, again, this is a talk about experiments with the definition. So this is our next experiment with, inferential privacy, okay, called profile-based privacy. So far we have been talking about central privacy, and in central privacy, the idea is that you have a bunch of users who trust the private curator, right? And then the private curator goes and gets their data. Then they sanitize, they don't have to sanitize the data, but, they can compute something on it. They sanitize the result of the computation, and then they just release it over the privacy barrier, right? And this is actually an excellent model for the census because, you are legally required. I mean, I don't know how much you trust the government, but you are certainly legally required to, right? I mean, it's supposed to be, my impression is that it's supposed to be like a felony to, I don't know if it's like, or a misdemeanor to lie to the census agent. I think, you could be punished for it if you lie to the census agent, but, I don't know if it happens in practice. But so you trust them, and then they output something. But more recently, a model that has emerged, especially in the industry, is, and I'm sure, well, what I am told is that you guys use this, is, I'm not the one who works in Google, is what is called local privacy, right? So in local privacy, what happens is that, imagine, I am the user, I have my mobile phone, and my mobile phone, kind of sanitizes my data before it sends it over to an aggregator. So, for example, my mobile phone could, I guess the kind of the canonical example is this Apple, is the Apple implementation, where what happened was that they were sending out some usage statistics, and what they did was they made each statistic private, and then they sent it over to Apple, and who was just aggregating it to figure out, how many people had, what is the, they figured out how common a certain bug was, right? And in local privacy, what happens is there is no trusted curator. So you are sanitizing your data before you send it out. And this, in fact, poses certain challenges, right? Because if you are doing local differential privacy, what you are doing, kind of the guarantee that you are offering is that, your algorithm applied to user one, the probability that your algorithm applied to, my data is equal to T is more or less the probability that, your algorithm applied to my data is equal to S for any S and T in the domain. Right. So for 0, 1, it's fine. But let's say, you might be saying something like, what I do is kind of indistinguishable. So let's say if you are sending out some behavioral data, what I do is indistinguishable from what somebody in India does. Right. And to make those, to make these things indistinguishable is a lot of noise, right? So, and especially because you are doing it at the individual level and then aggregating over there, it's a lot of noise, and which might, which leads to lower utility, right? And yeah, so which leads to lower utility. Right? And so one of the things that we've been thinking about is, can we get finer grained local privacy, right? So this is, something we've been experimenting with. So how could finer grain help? Well, the, kind of the intuitive idea is, this is coarse grained local privacy. The idea would be, if you look at the figure on the left, the idea is that all T in the domain are just blurred, right? And so this needs a lot of noise. Whereas with finer grain, what you might want to do is, if your T is in one of these gray balls, then you just blur all things in that gray ball. Maybe you blur all things in that other gray ball, and so on. And the idea is that as a result of this kind of finer grain local privacy, you might need less noise. And this kind of idea has been there, right? I mean, before our work also, I mean, there's been some, in 2012, there was some work on edge, like feature differential privacy, this kind of thing, feature level differential privacy. Actually, one solution which is extremely popular uh, about blurring close by points is something called geo-indistinguishability, right? So there the idea is that my location is private, but up to a certain radius. So I may be okay with Google knowing that I live in San Diego, but or Google's app knowing that I live in San Diego, I may not be okay with them knowing that I live in this particular building, right? So that would be an example. So that is kind of what geo-indistinguishability does. It blurs people's location within a certain radius, right? And there are many other work. And what our work does is, so this was a paper that appeared in 2019 ISIT. And what our work does is that it tries to get into a more general framework for this sort of thing. Okay, so how do we model this? Well, we model this through something called profiles, and our definition is known as profile-based privacy. So what is a profile? Our profiles are a possible set of, events, or, I don't know if I want to call them events or things that you want to be kept secret. And it's modeled by a distribution PI. Right? So an example could be, let's say, and I chose an example specifically in the Bay Area for this talk. Let's say, you live in Berkeley Street A, and you commute to San Francisco, and versus, so that could be your profile, right? That, distribution of trajectories from Berkeley Street A to San Francisco, right? So that could be your profile. And what we also have is what is called the profile graph. So a profile graph is a graph, right, where each node is a profile, and an edge connects pairs of profiles that you want to be indistinguishable. So, for example, let's say you live in Berkeley Street A and you commute to San Francisco, and maybe what you want is you want to be indistinguishable whether you live in Berkeley Street A and commute to SFO, or you live in Berkeley Street B and commute to SFO, right? You may want these two pairs to be indistinguishable, right? So these could be distributions over trajectories, and you may want them to be indistinguishable. Okay. And that gives rise to the definition. If you have, PI, so for all edges, PI, PJ in your graph, probability that A of, so remember PI is a distribution. Your algorithm takes in X and PI, right? Probability that X and PI is equal to Y, conditioned on X being drawn from PI, over the probability that A of X Pj is equal to Y, conditioned on X being drawn from Pj. That is as most e to the epsilon. And here again, epsilon is the privacy parameter. And and this has, of course, various relationships to other definitions. This is a special case of a local version of what is called pufferfish privacy. So, I don't want to get into what pufferfish is. I'm sure most of you know about it, but it's a form of inferential privacy. So the difference between this and pufferfish is that this is a local version, right? We are looking at each individual's data. And in the local version, this makes a little bit more sense because, if you are sending if I am sending some data, based on my mobile phone, my mobile phone or Google knows a lot about me anyway, and I am just trying to kind of blur out some information. And this is essentially a special case of local pufferfish, where the secrets are data generating distribution. This is also closely related to blowfish privacy, where the idea is that but blowfish is again a special case of pufferfish, but it's a centralized model, and their secrets are less general, whereas our secrets can be a bit more general. And it's, again, as I mentioned earlier, that it's also very closely related to geo-indistinguishability. And in fact, geo-indistinguishability is just a special case of profile-based privacy, where the idea is that your profiles would be locations, distributions within a certain radius, right? That would be, that could be. So that it's a special, geo-indistinguishability is a special case of this. And it's also related to a work by Lalita's group, which is called max leakage constraint hypothesis testing, where I think what happens is they have a similar setting, but we have somewhat different goals from them. So if you knew about some of these works, these are related but a little bit different. And so what about the properties? So what kind of properties can be retained for them? One of the interesting things that we can show is that it obeys post-processing invariance. This is not super duper interest. I mean, this is like, okay, let's just say this is not super duper unexpected, given that, we are still retaining this max divergence. And we can show, so we can show post-processing invariance. For graceful composition, remember that there are, two different kinds of composition, right? So sequential composition says that multiple uses of the same sensitive data gives you a slow privacy decay. Parallel composition says that multiple uses of disjoint data leads to the same privacy, right? But for local, this kind of a local inferential privacy model, things are actually a lot more complicated, right? And we can show, so the analogs of sequential and parallel are actually a lot more complicated, because the profile, you also have to take into account the profile selection, right? So you have to take into account whether the profile selection, so you are selecting a profile, then you are drawing something from the profile, you are, then you are releasing a sanitized version of that, right? So here things are complicated because the profile selection adds some extra dependence. In fact, what we can show is if the profile selection is independently done, then you can get parallel composition style results. If you know that you are selecting the same profile, then you can get sequential composition style result. But if the profile selection between, different iterations are done in like super complicated ways, then you may not, then we can't show anything. And, so for example, what could happen is, let's say today, that, so for example, kind of the bad case is that if you have an adversary who knows that, let's say I have some routine, right? So maybe today I go to, I have some routine. They know that on Monday, Wednesdays, and Fridays, I go to UCSD, but on Tuesdays and Thursdays, I go work at a coffee shop. Then, they can exploit that information. They can exploit that stuff. And so my profile on, Mondays is something, and on Tuesdays is something else, and on Wednesdays, it's exactly like Monday. If they know this kind of information, then they can, get more confidence. And this is a case in a lot of, inferential privacy style results. So what about mechanisms? So let me show you kind of, the simplest discrete setting. Let me show you some simple mechanisms. So let's say we have, the simplest discrete setting, and we have and our profile graph is just two profiles, PI and PJ. Under PI, so what we are doing is we are observing a single bit. Under PI, the probability that that bit is 1 is, little pi, and under PJ, the probability that that bit is 1 is little pj, right? And your mechanism in this case is, one of the simplest things you can think of, randomized response, you will just flip your bit with probability p, right? So how do you pick the probability of flips? Well, if you pick a low p, then you will get high utility, right? Your bit would be the same every time, would be quite close to what it was before, but it may violate privacy. Okay. So how do you find p? And as it happens, you can find p for profile-based privacy. You can find p by solving a linear program. And the linear program is basically where you can express your privacy constraints, which guarantees you profile-based privacy. And as it happens, after a lot of algebra, well, after some algebra, what you find is that these privacy constraints become linear constraints. And then you want to just maximize utility, which is minimizing the flip probability, right? And, you can do this by solving this problem. And this is basically what we call the one-bit mechanism. Okay. And you can also, you can extend this to, it's a more complicated optimization problem, but you can extend this to, other stuff, right? So you can extend this, if you have a clustered graph, you can have the one-bit cluster mechanism. You can use the highest p for any edge, and you can extend this. And again, you can do maximize the utility subject to these linear privacy constraints.
Just a time check. We have around 5 minutes.
Okay. So we're almost there. So for categorical, again, you can extend this to more general graphs. You can extend it to key categories. And what about utility? Well, you can also, for one bit, this is kind of the simplest thing. Even in the simplest case, for the one bit mechanism, let's say these flip probabilities, these probabilities are pi and pj, then your flip probability, you can show that it would be less than equal to pj minus pi divided by 1 plus e to the epsilon. Whereas for the corresponding local dp mechanism, you would, your flip probability is 1 over 1 plus e to the epsilon. Right? So when pj and pi are closer than 1, like if your pj is 1, pi is 0, that's it. If they're closer than 1, then you can get an improvement. And these are some simulations. That's the basic idea. If your profiles are really far apart, of course, if you have to blur things that are really far apart, you're not going to get much improvement. But, as they come closer together, you get more of an improvement. So in conclusion, we talked about, a form of basically these are some experiments with privacy definition. We talked about a form of differential privacy against capacity bounded adversaries, a form of inferential privacy for the local setting, and we can get mechanisms with, we explored how to get mechanisms with better privacy utility trade-offs. Okay? And I guess these are the references. And I'll just stop with my co-authors, especially Jacob and Joseph, who were my students. And Joseph was my student; he's just graduated, and Jacob is still my student, and Ashwin is my collaborator. Thank you.
Thank you, Kamalika, for this amazing talk. I guess we have a few minutes for questions. So I have a question. My question is like, when we go into this kind of, even if we just, so first question is like, does this guarantees extend to approximate versions of privacy? Not, let's say not any differential privacy, but something like PTR or this kind of mechanisms, will they be captured by this sort of definitions, or can?
So my question is that inferential privacy is complicated for approximate.
I see.
The Rennie is fine. Rennie goes through. I mean, you would just get some, approximate prior would be equal to, some weighted averaged prior knowledge would be equal to weighted average posterior knowledge. But additive delta is what you mean, right? Approximate privacy and PTR. My impression is that is a bit complicated for inferential. And in fact, I think of it as an open question. We don't exactly know what happens. I think, if we are thinking about a theory of privacy definitions, trying to figure that out would also be quite interesting.
I see. I guess we are almost out of time. So this was an amazing talk. Let's thank Kamalika again.